Okay, there we go. Good afternoon, everyone. My name is Greg Hankins with Alcatel-Lucent. I'm going to talk to you about the evolution of Ethernet speeds, and I always like to start with a historical picture. And this one is from, let's see, it's hard for me to read my slides over there. I think from the early 70s. So the point is that Ethernet as a technology is over 40 years old today. So it's kind of amazing that a technology that old is still widely used and very popular and being actively developed for use on the internet today. So this presentation is one that I've given many times, and I always have a number of updates. So there's always new material as there are new developments with Ethernet in the IEEE. And this presentation is also very dense. There's a lot of content in it. So it's intended mostly to be used as a reference. So I'm not going to go over every detail in the presentation, and I'll try to do my best to speak slowly because I know that there are a lot of acronyms and it's very difficult for the translators to keep up. Okay, this is what we're going to talk about, the Ethernet speed evolution, and then there are a number of new speeds that are being developed, so we'll talk a little bit about each of these: 2.5 and 5 gig, 25 gig, 40 gig, 100 gig, and 400 gig. If you look at the development for Ethernet, over the past several years, we've done a number of speeds. We've done 6 speeds over the past years up until now, and we see different requirements for Ethernet technology for different applications. We see different requirements in terms of speed, density, pricing, cost, things like that. So this has led us to develop a number of new Ethernet speeds that are targeted at specific different applications. And you look at the past and the present, what we're working on right now, we have the potential to deliver up to 6 new speeds in the next several years, which is the same amount of speeds that we've done in the past 30 years. So it seems like there's a lot going on and a lot of different speeds being developed for different applications. This is the target applications. It doesn't mean that the technology will exclusively be used there, but this is where we think that the technology will be most useful. 10 gig Ethernet obviously is very popular in every part of the network. We have 2.5 gig Ethernet and 5 gig Ethernet, which is driven primarily by the demand for wireless networks, also the large installed base of Category 5 cabling, and the new requirement that's very interesting is also for hard disk drive interfaces. 25 gig is being developed for server aggregation, so this is a top-of-rack switch to server NIC interface. 40 gigabit Ethernet, there's not a whole lot new with 40 gig Ethernet. It's a very mature data center technology now. 100 gig Ethernet obviously is a big development and a big focus, and then 400 gig Ethernet for high-speed backbone networks is coming in the future. So let's go into detail about each of these technologies a little bit. There's 2 market drivers for 2.5 and 5 gig, and it's very simple to see. The wireless speeds now on 802.11 wireless are reaching up to 7 gigabits, but the connection between the base station and the Ethernet switch is limited to 1 gigabit. So you can see that there's an obvious bottleneck there and that a higher speed is needed. So we even have high-speed wireless technology that's coming that can be up to 4 times faster than what we have today. So the rule of thumb is that the wired speed should be about 75% of the wireless speed. So you can see that this translates very nicely into 2.5 and 5 gig speeds for Ethernet. The other requirement, of course, is power over Ethernet, and that has to drive the power to these access points. The other driver for 2.5 and 5 gig is the large installed cabling base. So this is a US study that was done for a number of years that studied Category 5 and Category 6 cabling, and there are a number of different resources available, so I just use this example. But there's a very large installed base. I think my first job when I started working in networking was pulling cable. So I started doing this in the early 90s, replacing Cat5 cable in the building where I worked. And if you think of every building in Sao Paulo, every hotel and school and office building, shopping center, every building has Cat5 or Cat6. So we want to be able to reuse this technology and use a faster speed over it. The very interesting thing is that in this particular study, the data center was a small portion of this installed cabling base. So it really is a number of buildings that I just mentioned that has the large majority of installed cabling base. There's other applications as well. Wireless is the obvious one, but there's all sorts of high-definition security applications, obviously faster desktop or PC computer speeds, and things like that. In terms of developments, there's an active project in the IEEE right now. They're developing a standard for 2.5 and 5 gig over Cat5 and Cat6 cabling. And it's going to be a fast project. We already expect interfaces to be available sometime in the next year, 2016, when the standard is finished. For each of the projects, I have these reference slides, so it tells you where you can find information on what's going on in the IEEE, and you can. All these things are public. So if you're interested in what's going on, you can just go to the URL at the bottom of each slide, and that will tell you more about it. The other thing that's going on, and this just happened, so I just added this slide last week, is that there's a new study group in the IEEE that is looking at hard disk interfaces and the possibility to use Ethernet instead of SCSI or IDE or something like that. So this is interesting, and it has, I'm not a storage expert, but it has applications in something called object storage or object databases. And the idea is that you would have a very large array of disks that have a 2.5 or a 5 gig Ethernet interface that just connect to some sort of Ethernet switch directly, and then that eliminates the need for a storage switch or something like that. So that's very interesting, and like I said, this project just started in the IEEE a couple months ago. There's two industry groups that are driving and supporting 2.5 and 5 gig. There's the MG-based T Alliance, which was basically started by Broadcom, and then there's the N-based T Alliance, which is basically everyone else but Broadcom. So these groups were developing competing standards at first, but those standards have now been merged into one standard in the IEEE, and these groups are basically now just doing some industry marketing and things like that around the technology. Okay, let's go on to 25 gig. So there are a number of market drivers for 25 gig Ethernet, and the primary one is to provide a cost-optimized solution for connecting servers. So from the top-of-rack switch to the server interface. We have a number of 25 gig applications that we use already. We use it in 100 gig. We use it in a variety of electrical signaling to different types of optics. So it's not a new technology, but it turns out, and I'll show you this on the next slide, if you do the math, using 25 gig signaling works out a lot better than using 10 gig signaling because it's more efficient and it gives us better density. And then you say, well, what about 40 gig Ethernet? Well, that's a great technology. It has its own application in the data center, but there's also a need for different technologies such as 25 gig. And you also have to remember that 40 gig by now, we started working on it in 2008 or 2009. So the technology 40 gig is almost 7 or 8 years old by now. And as the technology changes, then we also change the technology and the speed that we're developing. This is a math slide, but it really explains why this works out. If you look at some of the new chips coming out, there's a lot of 3.2 terabit chips that will be available on the market right now. So this fall and probably also next year. And if you look at how the math works out, if we use 25 gig signaling, then we can actually use the whole capacity of the chip. Whereas if we use 10 gig signaling, it's very inefficient and we have a wasted capacity in the ASIC that we can't even use to put bits on the wire. If you look at the top chart and think about a very large data center, one that has 1,000 servers or 100,000 servers, for example, the number of top-of-rack switches or spine switches that are needed, you can actually reduce that dramatically using 25 gig while providing that full capacity and the full availability of the bandwidth. In terms of 25 gig development, there's really two projects going on. There's a 25G-based T project. This was just merged with the 40G-based T project in the IEEE, so it made sense to combine those two projects into one. And there's no delay or change expected in that standard for next year. And then there's a lot going on with copper and fiber optic. And I realize this is a very dense slide, so let me just spend a little bit of time on it. One of the challenges, and I have a little table on the bottom, one of the challenges with copper and short reaches is the forward error correction, also called the FEC or the FEC. For these kind of applications, people want a different bit error rate and a different FEC. The thing about FEC is it affects latency. So the more complicated error correction you have, the higher the latency. So the applications for the server that people are thinking of are real-time applications where they have very, very strict and low latency requirements. So some groups within the IEEE want a very low latency, which means no FEC or no FEC, and then some groups in the IEEE want a very good bit error rate, which implies a very complicated FEC, which means the latency on the wire is a lot longer. So all these projects for 25 gig copper are relations to 1 to 3 meters with a different FEC. So there's very different options for each of these types, and there are a bunch of different cable types that have been defined in the IEEE. There's also a 70 meter multi-mode interface that's being developed. This standard is moving along quickly as well. We expect it in September of 2016, and probably some interfaces on the market next year as well. There's the 25 gigabit Ethernet Consortium. This was founded before the project started in the IEEE, so this is an industry group that's also developing a 25 and a 50 gig Ethernet standard. Unfortunately, it's a membership organization and the standard is closed, so I can't tell you what's in it because I'm not a member, but they're developing a competing specification, and I hope that they end up merging their efforts with the IEEE because we really don't want to see two different standards on the market. This is the 25 gig technology reference slide. I have a slide like this for every technology. I typically don't talk through them because they're very, very boring, but they do list everything about the technology in one single place. So you can use this as a reference if you need to know anything about 25 gig Ethernet or any of the other technologies that I'll talk about. So everything is in one place there. Okay, moving on to 40 gig. 40 gig is a pretty mature market. We have a number of short and long reach interfaces. We have the QSFP Plus, which has been on the market for some time. It's also used for some other technologies. We have a number of different cabling options. The thing that's interesting and I think may have been a surprise to people was that the breakout was a big, very popular option. So 4 times 10 gig to 40 gig breakout is very popular in data centers and top of rack aggregation switches. And then on the 40 gig side, we have short reach multi-mode interfaces. We can go up to 40 kilometers on single mode now. So 40 gig as a technology is almost done. There's not much going on in the IEEE. We had the longer reach 40 kilometer interface that I just told you about was finished earlier this year. Then the other thing that's going on is the 40G base T, so that's a twisted pair interface for 40 gig. That standard will be done sometime early next year, and then I don't think there's going to be a whole lot of 40 gig development, so it's pretty much a mature technology and not much more to do for that one. Here's your technology reference slide that I'll just kind of skip over. So moving on to 100 gig, this is where it gets a little more complicated and a little more interesting. This is worth spending some time on. So if you look at the technology adoption curve for 100 gig, it's been very slow. It's been a lot slower, I think, than most people in the industry expected. And that's primarily because of the cost and the density. So when 100 gig came out in 2010, the idea is that it would be somewhat cheaper than a corresponding lag of 10 times 10 gig Ethernet. Turns out that didn't happen. It was actually more expensive than 10 times 10 gigs. So this really slowed the adoption. But over time, we've had a number of different technologies that have improved the cost and also the density of 100 gig. And in particular, and this year and next year is predicted to be a very big market for 100 gig for 2 reasons. The number one is the 3.2 terabit chips that I mentioned. So there's going to be a lot of these on the market in terms of blades for routers and switches, and also standalone switches with 3200 gig ports. So that's really good for density. The other thing that's helping that is new form factors. So we have the CFP4 form factor and also the QSFP28. These are very important form factors for 100 gig because they get us the density that we need. Before, the optics were simply too big to fit into the router for more than 4 or 8 ports. And if we look at how the market's evolving, sometime later in the next 2020, then we'll actually have what we call commodity 100 gig Ethernet that's available at very cheap prices like 1 gig and 10 gig is today. So the market is going to evolve over the next several years. Here's a fundamental challenge that we face when going from first generation 100 gig to second generation 100 gig. And it comes back to that signaling that I was talking about for 25 gig Ethernet. When we developed 100 gig, we reused the technology that we had available, which was 10 gig. So a lot of the first generation 100 gig implementations are built around 10 times 10 gig, just because that's what we had available when we were developing this back in 2006 and 2007. Now we have better signaling available, which is 25 gig, so we want to take all the 10 gig signaling out of 100 gig and replace it with 25 gig, which gives us a cheaper solution and also a higher density because the optics are smaller now. In terms of 100 gig developments, there's not a lot going on right now in the IEEE. The interesting things are really not so much as what happened in the IEEE, but the two projects that didn't happen in the IEEE, and I have another slide on that I'll show you. The challenge in the IEEE is that it's an industry standards group, so the way that decisions are made is by consensus. The group comes together, looks at all sorts of different technical solutions, and then chooses the best one by agreement and voting in everyone in the group. So the standards are actually voted on as opposed to just adopted without consensus. So there's a lot of work in the IEEE to build consensus and come to a conclusion as a group in order to develop a new technology. What's missing for 100 gig is a short reach single mode interface. So we have 100 meter interfaces, we have 10 kilometer and 40 kilometer interfaces. The thing that's missing is a 2 kilometer or a 500 meter interface. And this is in the middle, you can see there was no consensus in the IEEE, so this objective was actually taken out, and there is no standard for this short reach, 500 meters to 2 kilometers. Here's just a picture of the evolution of modules. You can kind of see we started out with the CFP, then we had the CFP2, and now, as I mentioned, the new modules that we're actively shipping are CFP4 and QSFP28. So if you kind of had to characterize them, I would describe the CFP4 as an option for longer range reaches. It has a higher power budget than the QSFP28, so the QSFP28 really was designed for short reach interfaces. So I think you'll probably see, in general, short reach interfaces on the QSFP28 and then longer reach interfaces on the CFP4. Here's maybe the most interesting slide in the presentation is how does this all relate to my iPhone? So you can see that on the one side, the CFP, the original CFP, is actually very large. It's larger than an iPhone. And then as the optics technology has evolved and gotten better and better, the optics have gotten smaller. So the CFP2 is about half the size of the CFP, and then the CFP4 is about half the size of the CFP2. And then the QSFP28 is just slightly smaller than the CFP4. So I have a bunch of pictures of them all stacked together, and the top one is the XFP, so the 10 gig XFP. So you can see that the 100 gig optics over the past years from 2010 until this year have evolved, and the optic size are getting close to the 10 gig XFP that we had. This is where it gets complicated. So because there was no consensus in the IEEE, a bunch of different industry groups went out and said, okay, there was no standard in the IEEE, so let's go out and do our own thing. So this is kind of like, well, some time ago, I don't know if you remember videotapes, there was a VHS format and a Betamax format. I don't know if that analogy works here, but it was two different competing standards, and one of them ended up winning. Well, the point here is that there's now 4 competing standards, and it's not clear who's going to win on this one. The other thing that this does is it divides the market into 4 different segments now, and each group has its own set of supporters and its own set of drivers. So for example, Microsoft is a big proponent of something called PSM4. This is running 100 gig Ethernet over parallel single mode fibers. So this is what they want for their data center, and this is what they've been pushing the IEEE. Other component vendors and other network operators and technology vendors want something different. They want a CWDM interface. So it's not clear who's going to win here, but I think the point is that the market cannot sustain 4 different segments. So something has to change so that there's only 1 or 2 different competing standards for a 100 gig short reach interface. And here's your technology reference, so we'll just skip over that. So what's next is 400 gig. This is another interesting one. So there are several industry challenges for 400 gig that we looked at in the IEEE. And the first one is that everyone asked, okay, we had an evolution from 1 gig, 10 gig, 100 gig, so everyone wanted terabit Ethernet. Terabit Ethernet sounds cool. I think it just sounds fantastic, sounds really cool. So everyone would love to do terabit Ethernet. The problem is that if we weigh out all the different options that we have, the technology options between the optics, the electrical signaling, and then all the market requirements with the cost and the density, doing terabit Ethernet with the technology that we have right now doesn't make sense. So we could build terabit Ethernet, but it would be so expensive and so cumbersome that no one will want to buy it. And if no one buys something, then there's no point in building something. So in the IEEE, we did a lot of studies and we came to the consensus that 400 gig actually made more sense as a next generation technology than terabit Ethernet. So that's why 400 gig was chosen as the next speed in the IEEE. There are a number of developments around 400 gig. This has been a very difficult one, and I'll tell you why on the next slide. So there are a number of short reach interfaces and long reach interfaces that are defined for 400 gig. There was a lot of discussion in the IEEE about the best solution, and the discussion went on, and it actually delayed the standard because there was no consensus on what the best choice was. So now we're expecting the standard sometime in the end of 2017. It was at the beginning of 2017. Now it's delayed by some time. So we'll see that at the end of 2017, and probably the first interfaces around that time too. And this is where it gets challenging. So with 1 gig and 10 gig, basically, if you just oversimplify it, what you're doing is you're blinking a light. You're blinking the light really fast, but it's just a blinking light at the end of the day to make that signaling work. With 100 gig and 400 gig, you're doing complex wavelength modulation and all these digital signaling and things like that. So it's much more complicated than just blinking a light. And you can see the different choices that we have. There's only 4 ways to go faster. You can actually change your signaling speed to go faster. You can change your modulation. You can change the number of fibers that you have, or you can change the number of waves that you have. And so this different combination led to many choices you can see on this table. All these were choices in the IEEE that were debated, and we had to come to agreement on what the best cost and what the best technology choice was for 400 gig. In the end, the ones that were in green, the green boxes, are the technologies that were chosen as the standard. But this is why there was a little bit of delay, because there was so much discussion about all these different options. And the thing about the IEEE is that component vendors and technology vendors and optics vendors, they have a solution in mind that they want to bring to market. So they're kind of competing different standards and competing different technical opinions in the IEEE, and this is where people have to come to consensus. There's already a couple of different pluggable modules for 400 gig. There's something called the CDFP, which is a short reach interface, and there's something called the CFP8, which is going to be a longer reach interface. This is about the size of a CFP2, and then you can see I left these blank, but as our technology choices get better and better, then we'll have something like a smaller optic, and then eventually, maybe sometime in 2020 or so, that's when we'll actually have 100 gig serial signaling. And this is when terabit Ethernet becomes feasible, or some sort of speed at terabit Ethernet. So we're looking at least 5 years before that actually is technologically and economically feasible. So what's next in the IEEE? As I showed you on the first slide, there's a lot of things going on. At the November meeting just last month, the IEEE started 3 new study groups that are going to investigate new technology. The first one is a 25 gigabit Ethernet longer reach interface. So if you remember from the 25 gig slides, the longest interface is defined to go up to 70 meters, so there's a desire to have a single mode 2 kilometer, 10 kilometer, maybe 40 kilometer interface for 25 gig Ethernet. The other things that are going on is that a 50 gig Ethernet study group was just formed, so this would be a single lane of 50 gig Ethernet. And this also affects another next generation Ethernet study group that was formed to develop a 200 gig Ethernet. So you can see that there's a lot of different technology choices that are already being developed in the IEEE, and 3 new groups that were just started in November that are going to be looking at these different speeds. So if you look at the futures, in the past, as I mentioned before, we had this expectation that we would have a very linear increment in speeds from 100 meg, 1 gig, 10 gig, 100 gig, but we kind of have to change our perspective, because with those increments, the expectation was that it would be 10 times the speed with around 4 times the cost. So for 100 gig, that clearly didn't work out because it was 10 times the speed initially for the first interfaces at about 10 times the cost. So those economics don't work. So what we've realized is that the speed increment, as we get into these faster and more complicated speeds, is about 4 times instead of 10 times. So that's why you see 100 gig going to 400 gig. And the next likely speed of Ethernet could probably be not 1 terabit, but 1.6 terabit Ethernet, so 4 times 400 gig. And then, of course, as I mentioned, we have the new technology for 50 and 200 gig that is being studied now. So if we look at the summary of everything that we've talked about, we're working on 2.5 and 5 gig, primarily for wireless applications and Cat5, Cat6e applications. 10 gig is very popular. It's used in every part of the network today. 40 gig is a very mature technology. It's increasingly deployed in data centers. The breakout option has been very popular, so 4 times 10 gig on a 40 gig interface has been very popular. 100 gig is now moving into second generation, especially with the new optics CFP2, CFP4, and QSFP28. And we're working on 400 gig right now, and Ethernet at terabit speeds, as I mentioned, will be worked on sometime in the next 5 years, maybe 5 or 6 years after 2020, when the technology actually becomes feasible. Here's a bunch of links to IEEE websites and the optics manufacturers' websites. You can go read those in your spare time if you want more information. And that's it for this presentation. I have about 10 or 15 more reference slides that are after this ending slide, so there's more material here if you want to download the presentation and look at all those slides, but I don't have time to go through them. So that's what we're doing for Ethernet. Anyone have any questions or comments?
Pessoal, vocês querem fazer alguma pergunta?
Okay. Hi, Greg. Thiago from Algar Telecom. I have 2 questions, actually. First, by the way, nice presentation.
Thank you.
And the first one is, we saw in 40 and 100 gigabit interfaces that there's a joint effort from IEEE and ITU-T in defining the standards to work together. And how is that going on for 25 and 400 gigabits?
Okay, so that's a good question. If I can summarize your question, I think you're asking how the interaction is between the Ethernet standards in the IEEE and the ITU standards.
Right.
Yeah, so there is a liaison between the ITU and the IEEE, and they have regular communication between each other. But obviously, you make a good point that we have to be able to transport the new Ethernet speeds in the ITU, in the ITU speeds that are defined. And sometimes the mapping between the two is different. So there's a translation, and I'm not an optical expert, so I don't have the exact detailed answer, but in general, for every speed, there is work being done between the IEEE and the ITU so that it maps into one of the ITU signaling hierarchies. So it will be possible somehow.
The second question is, in your opinion, what will be the next Ethernet speed? Actually, we heard a lot of people talking that going from 400 gigs to 1 terabit, it's a smaller step. It's not the effort. It's huge in research and development for just a small step. So, in your opinion, how do you see that will go?
It is. And it's a good question. So the question is, what is going to be the next Ethernet speed? So it's a challenge because you're right, it takes a lot of effort and it's extremely expensive for the component vendors to invest in this new technology. So I think in the next couple of years, as we've seen with previous speeds, we'll see link aggregation become very popular. So when we have 400, or even now with 100 gig, we have 100 gig, people are doing many different types of link aggregation to get up to a terabit of capacity. I think in the near term we'll see link aggregation used with 400 gig, and then when we have the technology to develop a faster speed, then we'll see a new native speed come out, probably 1.6 terabit Ethernet. But as with every speed in the past, link aggregation is very popular.
All right. Yeah. Thank you.
Bom, se nós não temos mais questões, I would like to thank Greg. Thank you very much.
Yeah. Thank you.